Hello and welcome to the flowering portion of the Citrus Flowering, Fruit Set, and Development short course. In this module, we will focus on flowering. We will define the different types of flush that can emerge, cover the differences between floral bud induction and differentiation, discuss factors affecting these processes, and lastly explore how HLB is affecting flowering in sweet orange. In sweet orange, the spring flush is highlighted by intensive flowering and vegetative flush. During this period, several different types of flush will emerge. Some will be purely vegetative and contain only leaves. Some will be leafy inflorescences that contain one or more floral buds and leaves. And finally, some will be leafless inflorescences and contain only floral buds. Keep these different types of flush in mind, as they will come up several times throughout this video as well in other videos. Now let's take a step back and see how these different types of flush are formed. Citrus buds experience a weak dormancy that must be broken for this new flush to emerge. These buds can be found at the base of mature leaves along green wood shoots. These shoots are generally less than a year old, and these dormant buds are vegetative by default, but several internal and external factors can come together to trigger a bud's transition from vegetative to reproductive. Induction describes the commitment of these buds to a specific bud type. Floral induction, therefore, describes the transition from a vegetative to reproductive bud. During this induction period, the bud itself will not change in appearance, but a number of changes at the molecular level will cause a shift in bud identity from vegetative to floral. So at the end of the induction period, the buds will still look the same, but they will be primed to form vegetative flush or either leafy or leafless inflorescences. Once induction is complete, the buds will begin to differentiate. Differentiation involves the actual formation of these different bud types. The first portion of this process is largely invisible and again involves microscopic changes. However, during the later half of the differentiation period, these changes become more visibly apparent as the buds develop. Soon you'll be able to visually differentiate between floral buds, leaves, and both. Conditions for floral bud induction are usually only present during the late fall and early winter, which is why the following spring flush is usually the only one to produce a significant number of flowers. Several factors affect the length of the induction period, the type of flush, and flowering intensity. This includes daily temperatures throughout the late fall and early winter, the length and severity of any water deficits, the carbohydrate balance, and the presence of hormones. We will discuss each of these in turn. Firstly, the changing temperature during fall and winter play an important role in breaking bud dormancy and regulating the shift from vegetative to reproductive growth. Specifically, the cooler weather during this period is needed to break bud dormancy. Generally, temperatures below 68 degrees Fahrenheit promote floral bud induction. Each hour below 68 degrees Fahrenheit contributes toward floral bud induction. These hours are called induction hours. Citrus buds will begin accumulating these induction hours around mid-November and continue to do so through the early winter. Generally, 600 to 900 induction hours are sufficient to induce flowering. At very low induction hours, you would get very little floral bud induction. Accumulation of additional induction hours will increase floral intensity and increase the ratio of leafless to leafy inflorescences. Essentially, at low induction hours, you could expect a mixture of vegetative and leafy inflorescences. With more induction hours, more leafy inflorescences can be expected, along with leafless inflorescences. With even more induction hours, you would continue to see a shift towards even more leafless inflorescences. However, this is not the only period during which temperature will affect the leafiness of an inflorescence. Even if very high induction hours are accumulated, high temperatures during bud sprouting can also increase the leafiness of an inflorescence. Warm weather is also needed to induce flowering. So after induction has been triggered by the accumulation of induction hours, a warm period lasting 7 to 12 days triggers the start of differentiation. The length of this warm period will vary based on the number of induction hours accumulated. The more induction hours that have been accumulated, the shorter the warm period needs to be. The entire differentiation process usually takes around 60 days and involves the formation of the floral bud and the transition to an open flower. Cycles of cool and warm weather lead to multiple waves of flowering. We can usually expect 2 to 3 waves of flowering here in Florida, with peak flowering falling between mid-February and April. Careful monitoring of fall and winter temperatures can aid in predicting the number and timing of flowering events. The University of Florida offers a flowering model that uses observed and predicted weather patterns to aid in predicting bloom dates. You can find the link to the model on screen and below, as well as a QR code on the screen that will link you to the site. On the Flowering Monitor site, you will be asked to fill in some basic information along with the current date. This information is used to guarantee the most accurate prediction for your field site. We'll now walk through an example of how the flowering model monitors the accumulation of induction hours and predicts bloom dates by looking at the 2021-2022 induction and flowering period. On the left, we have the information entered into the flowering monitor model. In the graph on the right, dates can be found at the bottom along the x-axis. The number of induction hours accumulated are along the axis on the left-hand side. We'll ignore the right-hand axis for now. Here we can see that by November 1st, 2021, 97 induction hours have already accumulated. By November 15th, we're up to 290. By November 30th, 525. By December 15th, we've reached 712. Notice we are now within that range of 600 to 900 hours that is sufficient for flowering. If we move forward to December 30th, you'll see we're up to 915 hours. You'll also see a whole new line has been added to our graph, and that differentiation and bloom dates have been added to the top of our graph. This is where the axis on the right-hand side comes into play. This axis monitors the degree of differentiation, or maybe put more simply, the degree of flower opening. The top of the line represents 0% differentiation, or the initial transition from induction to differentiation. As the line moves down to 100% differentiation, this moves us through the stages of bud formation and elongation and eventually to fully open flowers. In other words, this differentiation line serves as a bloom prediction line, with 100% differentiation representing full bloom. The new information at the top of the graph tells us when differentiation was determined to start, December 5th, how many induction hours were accumulated prior to the start of differentiation, 640, and lastly, when the predicted bloom date is, February 2nd. As we discussed, differentiation takes around 60 days, so the bloom date falls roughly 60 days after the differentiation date. However, the date will shift slightly based on current temperatures. Cool weather will slow the differentiation process, while warm weather will speed it up. You'll notice the bottom half of the differentiation line is blue. This is to indicate the predicted timeline for bloom based on current weather forecast. As we continue to move through this example, you'll see that the blue prediction line will vary slightly as new weather forecasts are made. Similarly, the bloom date will shift slightly as a result. Now, let's move on to January 7th, where we have accumulated 1,016 induction hours. Here we see another bloom prediction line has been added, suggesting we'll see 2 waves of flowering this year. The information at the top of the graph has also been updated to reflect the differentiation start date and predicted bloom date for the new flowering wave. You'll also notice the predicted bloom date for our first wave has changed as well, reflecting updated weather forecasts. Moving to January 15th, we're up to 1,150 induction hours. We see yet another bloom prediction line has been added, suggesting we will see 3 waves of flowering this year. The information at the top has again been updated. As we continue to move forward through January 30th, February 15th, February 28th, and March 15th, we see that the induction hours continue to accumulate. The predicted bloom dates also shift slightly with shifting weather conditions. Through this walkthrough, we've seen that multiple waves of flowering can arise as the season progresses. It's for this reason you should check the model regularly as the flowering season approaches, so that you can have the most accurate predictions for the coming season. Having an idea of when flowering will peak can help in scheduling sprays and other cultural practices. Next, let's take a look at the weather data during the induction hour accumulation period to see how temperature was affecting differentiation start dates. In this graph, the dates can be found on the bottom x-axis. The maximum hourly temperatures are measured along the left y-axis. The jagged black line represents the maximum hourly temperature throughout the whole induction hour accumulation period. The two dotted red lines represent temperature cutoffs. The top line is at 75 degrees Fahrenheit, while the bottom line is at 68 degrees Fahrenheit. Now let's overlay our flowering model. Here, the blue line represents the induction hour accumulation, while the three purple lines represent the three bloom prediction lines. If you'll notice, the start of our first bloom prediction line corresponds to a longer period of warm weather. Similarly, the second bloom prediction line corresponds to another, yet slightly shorter, period of warm weather. And our last bloom prediction line corresponds to a final short period of warm weather. This lines up with what we discussed earlier. As more induction hours are accumulated, less warm weather is needed to trigger the start of differentiation. Now we've come full circle and seen how both cool and warm temperatures play a role in floral bud induction and differentiation. Now let's move on to our next topic, how drought stress can induce flowering. Drought stress has been previously used to manipulate when flowering occurs in tropical regions. As we will see in the figure on the right, differentiation only begins once the drought stress is relieved. In this way, drought stress will delay flowering until regular watering has been reinstated. This can be very difficult to implement, as the response is highly rootstock dependent. Each rootstock is unique in their ability to tolerate a certain degree or length of water deficit, so deficit treatment would need to be tailored to each scion rootstock combination. Not to mention, the severity and length of stress matters. A continuous moderate water stress for as little as 2 weeks can be sufficient enough to induce flowering, but the effect is much stronger if prolonged to 5 weeks. However, perfecting the level of water stress can be a very dangerous game to play. Too mild of a drought stress will result in a very weak flowering response. Too severe of a drought stress will result in a largely leafless flower production, but will also lead to significant leaf drop. Let's take a minute to look at the possibility of using drought stress as a means of controlling flowering in the era of Huanglongbing, or HLB. One of the symptoms of HLB is significant root dieback. As a result, HLB-affected trees have smaller root systems than their healthy counterparts. When watered with the same amount of water, the HLB-affected trees' root systems will not be able to take up as much water as a healthy tree. This limited uptake capacity makes HLB-affected trees more susceptible to drought stress. HLB severity is also highly variable within a grove, which makes implementing a uniform stress very, very difficult to do. It's for these reasons that using drought stress to manipulate flowering is not recommended in HLB-affected citrus. Using this method will likely do more harm than good. Next, let's discuss the role of carbohydrates. The carbohydrates formed as a byproduct of photosynthesis provide the energy needed to support plant growth in the form of carbohydrates, such as sucrose or glucose. During the winter, growth tends to slow, while leaves continue to photosynthesize. This allows carbohydrates to accumulate during the winter. In the figure on the right, we're looking at the carbohydrate levels in older mature leaves, the orange line, new flowering leaves, the green line, new vegetative leaves, the red line. In the older leaves, we see that their carbohydrate levels increase during the first few weeks of the year, peaking right before bloom. We then see a rapid decline in carbohydrate levels as flowering takes place. The carbohydrates continue to decrease as the fruits set and develop, but we'll talk about that more in another video. The main takeaway here is that flowering is a very expensive process. A very loose positive correlation exists between carb levels in the older leaves and the degree of subsequent flowering. Generally, it seems a minimum carb threshold must be met for flowering to proceed, but further increases in carbohydrate level don't always cause an equal increase in flower numbers. The actual floral intensity seems to be fine-tuned by other factors, but for now, let's dive a bit deeper into the carbohydrate economy. During photosynthesis, leaves produce sugars that can be converted to starch, which serves as a storage form of carbohydrates until they're needed. Or these sugars can be utilized to support all manners of plant growth. As leaves serve as the site of production, they are considered a source of carbohydrates. The organs that import carbohydrates for utilization, whether it be new flesh, roots, or fruit, are considered sinks. the movement of carbohydrates from source to sink is critical for new growth. In a healthy tree, carbohydrates are able to move freely through the phloem from the source leaf to the strongest sinks, allowing for normal growth. However, in HLB-affected trees, this movement is hindered. As part of the tree's defense response, the phloem is plugged to prevent the movement of the causal bacteria. But this also disrupts the movement of carbohydrates through the phloem. This leads to an accumulation of starch in the leaves and a shortage of carbohydrates in the sink organs, leading to carbohydrate starvation in the weaker sinks. Regardless of tree health, there's always competition between the sink organs for available carbohydrates. New vegetative flush, reproductive growth, and root growth will all compete for resources. One of these can only thrive at the expense of the other. For example, in order to prioritize flowering and fruit development, vegetative flush and root growth would have to decrease. Let's look at an example of this payoff in the alternate bearing pattern seen in some citrus species. On the left, we have a tree in its off year, and on the right, a tree in its on year. The tree in its off year produces significantly less flowers than the tree in its on year. As a result, the tree in its off year has less fruit set than the tree in its on year. However, because the tree in its off year has less fruit, it can invest more carbohydrates into its summer and fall vegetative flush than the tree in its on year. At harvest, the off year tree will have lower yields than the on year tree. Once the new season starts, the trees flip. The tree finishing up its off year now begins its on year. The off-year tree was better able to accumulate a reserve of carbohydrates for the new season, resulting in much higher flowering for the new season. This is due in parts to the lower fruit load requiring less carbohydrate investment and the increase in summer and fall flush that increases the leaf area available to photosynthesize. Likewise, the on-year tree drained its carbohydrate reserves, so it will not be able to flower as much in the new season. While alternate bearing patterns are usually not an issue in sweet orange, and especially not in the age of HLB, this relationship between previous season and current season is still relevant. If you see an unusually high yield one year, don't expect the same thing the following year. In the previous example, we briefly mentioned that vegetative flush increases the photosynthetically active leaf area. This brings us to our next topic. How canopy volume and density affect the carbohydrate balance? This relationship is quite simple. Relatively smaller or thinner canopies have fewer branches, so there's less available wood for new growth. The fewer branches also lead to fewer leaves available for photosynthesis and carbohydrate production. In this way, canopy volume and density largely control carbohydrate production and availability, which in turn affects the degree of flowering. This is a major concern in HLB-affected trees, as these trees do experience quite a bit of canopy dieback. If we look at the figure on the left, we can see a portion of the canopy of an HLB-affected tree exhibiting mild symptoms. The figure on the right depicts an HLB-affected tree exhibiting severe symptoms. By comparing the two, we can see just how thin the canopy of an HLB-affected tree can become as the disease progresses. In these two figures, I'm also demonstrating the frame method we use to monitor flowering. We hold these frames up to the canopy and count the number of buds, flowers, and fruitlets that fall within the confines of the frame. Doing this multiple places around the tree can give us a good idea of the floral intensity on a whole tree scale. As I'm sure you could guess, the mild tree on the left will have significantly more flowers than the severe tree on the right, simply because the mild tree has a much denser canopy. You'd be correct. In the graph on the right, the date is along the x-axis and the number of flowers on the y-axis. We counted flower numbers using the frames method you just saw. Following these trees throughout the whole flowering period does show that mildly symptomatic HLB-affected trees, the blue line, do produce more flowers than their severely affected counterparts, the orange line. And this difference is largely due to the major differences in canopy density and volume. Simply put, mild trees have more branches available for flower production and more leaves to support flowering. Now let's move on to our last major topic, hormones. Gibberellic acid, or GA, is the major hormone controlling flowering. GA acts by promoting vegetative growth over reproductive growth. Mature fruit produce GA that is then exported to the surrounding nodes. This in turn promotes the buds at these nodes to produce vegetative flush instead of floral buds. In the absence of mature fruit, there is no GA production, so the nearby buds are free to form floral buds. GA's inhibitory effect on flowering and promotion of vegetative growth has led to its popular use as a plant growth regulator. It has lately gained an increase in popularity as a means of promoting canopy recovery in HLB-affected trees. By shifting the balance of reproductive and vegetative growth towards vegetative growth, HLB-affected trees are able to recover some of their canopy without major losses in yield. Let's take a look at GA applications in practice. In a simple study comparing flowering in trees treated with GA to an untreated control, we can see that the GA-treated trees have lower flower numbers and have a slightly narrower flowering peak. GA applications must occur during the induction period to influence flowering. The timing and number of applications will also affect if the flowering window is narrowed, the intensity lessened, or some combination of both. In this figure, we will be comparing the flower numbers between multiple different GA applications and an untreated control. The GA applications differ in their timing and in the number of applications. Earlier applications, such as in November and December, tend to narrow the flowering window more so than decrease the intensity, whereas later applications, such as in January or February, tend to greatly decrease the number of flowers without affecting the length of the flowering window. And applying GA at 2 times seems to compound these effects. We've touched on HLB several times throughout this video, but let's take a moment to recap the HLB relevant points. We discussed that HLB-affected trees are more susceptible to stress, particularly drought stress. Their comparatively smaller root systems limit their ability to uptake water, making them more susceptible to any water deficits, regardless of if they are naturally occurring or implemented. We also looked at how phloem plugging slows the spread of the causal bacteria, but also affects the movement of carbohydrates. This leads to starch accumulation in source tissues and carbohydrate shortages in sink organs. We also looked at how HLB-affected trees experience significant canopy dieback. We then discussed how this canopy dieback reduces canopy density and volume, ultimately limiting the number of branches available to support flowering. Lastly, we discussed GA applications as a potential therapy for canopy recovery. The increased occurrences of secondary stresses, the carbohydrate imbalances, and the canopy dieback all lead to less flowering in HLB-affected trees, as we saw in this graph from earlier comparing mildly and severely symptomatic trees. When compared to healthy trees, the flowering window is prolonged, so you don't always see a sharp peak in flowering in HLB-affected trees. Before we wrap up this video, let's review the major takeaways from this section. The number of induction hours received during the late fall and early winter greatly affect the degree of flowering. Drought stress can be used to control the timing and degree of flowering, but is not a recommended practice in HLB-affected trees. Carbohydrate levels also regulate the extent of flowering and are responsible for the alternate bearing patterns seen in some citrus varieties. GA produced by mature fruit inhibits flower production on the surrounding wood. HLB-affected trees are more prone to environmental stresses, experience carbohydrate imbalances, and a significant amount of canopy dieback, leading to less flowering than would normally be seen in healthy trees. And that concludes the flowering portion of the Citrus Flowering and Fruit Growth and Development short course. Please refer to the Citrus Production Guide for additional information. The QR code on the screen will take you to the production guide. Thank you.